Well, it has to do with how can you um, uh, efficiently simulate the filling of an empty pipeline system. Yeah, um, so what we're interested in is, for instance, you have a fire water system which is dry, and then in case of an emergency, a pump ramps up. When the pressure is high enough, you open a valve and the system starts flooding. And hopefully you can put out the fire. That's the idea. But the problem here is that once the system starts filling with water, you get lots of momentum changes because the column of water is going through the system, and it also is going to slam into valves and nozzles and whatever. And you get quite a high forces acting on the system. Yes, these forces can be so large that they can actually cause damage, and there are lots of examples where we have seen that. So it would be nice if you could kind of predict whether a system is safe to operate, because you don't want a fire water system to crash at the moment when you need it. And so we were doing some research into some existing models, and one of them is so-called. Well, all of them are actually based on the concept of a volume that's kind of squeezed in between columns of liquid, and those columns can be either rigid or elastic, depending on how you model that. This is all nice, but we found out that all these models were created only to simulate the flooding of a single pipe, so it's quite limited. And we wanted to do something much more complex. We wanted to take a real fire water system with lots of branches, etc., and then have a reliable way of simulating that. Now, of course, we can resort to CFD. We can implement two-phase CFD models. That's a bit like using AI. You just throw more power at it, and hopefully you can get an answer out of it. But that's not what we were aiming for. We wanted to do it elegantly and have a much more efficient way to do that. Okay, so when you take a look at simulating transient events in pipeline systems, the workhorse there is the method of characteristics. This works quite well. It's a mathematical method. I'm not going to explain that here. It's kind of algebraic method also, therefore it worked very good. And so we wanted to have something that worked well all together with the method of characteristics. Actually, what we wanted is have another module that we can kind of tag on to the method of characteristics that takes care of modeling the movement of gas volume through your system. Obviously, we wanted to have it handle large and heavily branched pipelines efficiently, and also be able to track multiple volumes. Because if you get to a branch, a volume can break up into different parts that can travel through the system independently, and when they meet each other at the junction, they can kind of get together and then go on as a single volume. So we wanted to take all that into account. And last but not least, it should have some kind of acceptable accuracy. It doesn't have to be very accurate. Say 10-20% accuracy is good enough for our engineering purposes. Okay, so what we did, we took the elastic column model and then made some modifications on top of that. And we did that by assuming that the flooding happens sufficiently fast so that we can assume that the interface between the liquid and the gas is always perpendicular to the axis of the pipe. And so there are no mixed flow conditions that we consider. Either a point in a pipe is in the gas phase or it's in the liquid phase. We also assume that we have a single volume, and within that volume we have a single gas pressure. So we don't take the flow of the gas into account. Well, we also assume that everything is slow enough, and we also assume that air bubbles are not entrained in the liquid phase as it moves through the piping system. Well, this is something that's not completely correct, and I'll come back to that later on. Okay. Okay, so the model essentially starts with a number of volumes, and it's going to track how those volumes move through the system using the method of characteristics. So it uses the method of characteristics to predict the flow velocities, and using the flow velocities, it can predict how the volumes travel through the system. Well, that's not all, because a volume can also change in size because of the expansion and compression of the gas. It can also enter the system or leave the system through air valves, nozzles, or whatever kind of other outlets and inlets you have. And of course, the liquid interface moves also. So these are three aspects. They affect the size of a gas volume. And if you write this down in a mathematical way, you get to, in the end, a nonlinear system of equations involving the pressures inside the volumes. And we can solve that at each time step. So at each time step, we solve the pressure. And once we have that, we can move the interfaces and then track the volume throughout the system. We can be a little bit smart. So if all the inlets and outlets are connected to the same ambient pressure, we can all kind of grab them together and can handle them as a single inlet or outlet. Okay. Now, so each volume consists of one or more what we call segments, and a segment is just a volume of gas within a pipe section. And each volume, each of those segments is delineated by two interfaces, and what we call a positive and a negative interface, and we keep track of all that. So essentially, what we have is a graph where we connect all the segments to each other at the junction, because the junctions are the points where the different segments are combined into a single volume. So essentially, it's just a bunch of manipulations to track all these volumes going through the system. Now, the most difficult part is always at the junctions, and we can consider two cases. One case where a junction is in the gas phase and a water column is approaching. In this case, the volume will be broken up into two parts. So first you had those two segments that were joined into a single volume, and when the liquid starts to flow into the junction, those two segments are taken apart and they go on as separate volumes, so they can also have different gas pressures. Now, in order to calculate the initial flow rates in those two branches, we take a look at the moment, the moment of inertia of the fluid, and we try to minimize the change in the moment of inertia, because the fluid has a tendency to go straight forward. So we take a look at the geometry of the junction, and then based on that, we calculate the initial flow rates. Now, the second situation that you can have is that gas is flowing into a junction that was first filled with a liquid. This is a bit simpler to deal with because there is no new volume created. You only have to create new segments in those two branches. So at this point, that point, and you just add those two segments to the current volume of your system. Okay, so one of our goals was to limit the amount of computational effort. And I think that went quite well, because if you take a look at those two little, the one on the right is not so little, but the one on the left is a simple pipeline system. So for that system, you have a single volume to track, and you only have an overhead of about 22%. And for a very complicated geometry like that one, so this is a fire water system on top of a large oil tank, I think. With lots of branches and lots of sprinklers also. You have a slightly higher overhead, but still it's very acceptable. If you would want to do this with CFD, it would take a very large amount of time. Yes, Mick, you have a question? What do you do with overhead compared to what? Yeah, so compared to a simple method of characteristic calculation. So a simple transient calculation where there are no volumes at all. Yeah. Does it work? Well, obviously, we compared it with different experiments that we found in literature. This is one experiment where we have a long pipeline, which is initially filled with, or part of it is filled with air. And for that system, they measured actually the speed of the liquid gas interface, and you can see that our method tracks it quite well. You can see that it goes up quite rapidly, because initially there is very little flow resistance, so little friction, because the amount of liquid is quite limited. And as it starts flowing through the system, you get more and more friction, so you the flow velocity goes down. This is another series of experiments, a slightly different setup, where we compare the results to another model and also to experimental data. You can see that, well, the circles are the ones coming from our model, and especially for larger air pockets, we get quite good results. For very small air pockets too. In between, there is a deviation from the experiments, and we think it has to do with the fact that you get kind of mixed flow conditions at the outlet at that particular frame, at that particular point, which is not quite. Yeah, of course, we don't handle that. We assume that the interface is always perpendicular to the pipe axis. This is another experiment, so here you can see too that it matches quite well. And then we have some more experiments here. Yeah, so this is another entire series of experiments where we change the diameter of an orifice with respect to the diameter of the piping, and you can get all these results. Now, one thing that is of interest here is that in order to get to match the actual results here, we had to make some modifications to the wave speed. And so, why is that? Because when the liquid gas interface travels through your system, it's very, you can assume, of course, that little bubbles will be present at least in the first part of the liquid column as it travels through the system, and especially when you have lots of bends, etc. There will be some mixing there, and those bubbles, they have a higher compressibility, so they effectively lower the wave speed of your liquid. And in order to match these results, we also had to lower the wave speed in order to take that into account. So this, I think, is the largest drawback of our model, is that we don't do this at the moment. So this is all available in our commercial software package called Boss Fluids. We don't model the entrapment of air bubbles in the liquid column as it goes through the system. So, well, on one sense, that's fortunate because you get conservative results, because a higher wave speed results into higher pressure surges. But of course, it can be a little bit too conservative. So this is something that we're still working on and trying to see if we can improve on that. And we're also trying to use this model at the moment to build a better cavitation model. So there are a number of cavitation models, but they are all kind of implicit in the sense that they don't really track a vapor cavity through a system. And by using this method, we might be able to do that in a much better way. Okay, that is some other experimental data. Yes, so some concluding remarks. Yeah, we have kind of robust implementation, which is actually being used for 1 or 2 years already, also by commercial companies to simulate the filling of firewater systems, essentially. It's quite robust. I mean, we can handle quite complex geometries. It's also fast. And we're still working on the inclusion of air entrainment models. And so hopefully we can get some experimental data that we can get some correlations for, say, flow rates, geometries, etc. And then we can take that effect into account to make it more accurate.